Okay, so let's take a look at section 2.5. So a function of two variables, g, x, y, is homogeneous of degree n if g of tx, ty equals t to the n g x, y for all t greater than 0 and x not equal to 0 and y not equal to 0. So let's look at some examples of homogeneous functions. Okay, so for first example, say g of xy equals x squared plus 3xy. Let's now compute g of tx comma ty. Let me do it here. So we get then this, so g of tx comma ty. That means I'm going to put in place of x here, I'm going to put tx. Let's do that here. So it'd be tx squared plus 3 times x, but x now is tx, times y, but now y is ty. So I get this, and notice here, if I simplify this, I'll have then t squared x squared plus 3 t squared y. I can factor out the t squared, and I'll have with then x squared plus 3, sorry, missing an x here, 3xy, and that equals then x squared times g of xy. So we've shown then it's homogeneous of degree 2 because there's a 2 on this. And pretty much, if you think about it, a function will be homogeneous of each of the terms. So here, this term has degree 2, this term has degree 2 also. So as long as all the terms have the same degree, it will be homogeneous. So let's look at another example. So this next example, you have 2x to the fourth minus x squared y squared plus y to the fourth plus 9 x, should be times y here, times y. Now each of these terms is degree 4. That's degree 4, that's degree 4, that's degree 4, that's degree 4. So this should be homogeneous of degree 4. So you can check here if you did g of tx ty, you verify, if you work it out like we did up here, it should be t to the fourth times g of xy. Okay, let's look at one more example. Okay, so g xy equals ln of x squared over y squared. Okay, it may not be obvious, but this will be homogeneous also. Let's just show it here. So let's plug in tx ty here and see what we get. So doing that, we get then. So again, we're going to put tx in place of x, so it'll be tx squared. Ty in place of y, so it'll be ty squared. So simplifying this then, it's become then, ln of t squared x squared over t squared y squared. T squared will cancel, so it's become then ln of x squared over y squared, which equals g. We might say, well, there's no t to the n in front. Well, you can think of it as like a 1 here, so you can think of it as t to the 0 then if you want. So you can write it as t to 0 g xy. Okay, so it'd be homogeneous of degree 0, this one. Let's look at one more example. Okay, so our last example, gxy equals 1 over x squared plus y squared. So let's verify that this is homogeneous. So let's stick in tx, ty over here. So doing that, we get then. Okay, so I verified here. So we're going to put t of x in place of x. So it'll be t of x squared. Ty in place of y, so it'll be t of y squared. I can then pull out the t squared down here. I can write the 1 over t squared as t to the minus 2. then what's left will be this guy, so it's t to the minus 2 gxy. So this is also homogeneous, so this would be degree, I guess, minus 2 if you want to say. That's fine. Okay, now let's look at theorem 3, which is involves solving differential equations that have homogeneous functions. So let's look at that. So theorem 3. So I'm going to erase this stuff now, and we'll go on to theorem 3. Okay, so here's theorem 3. It says if m is a function of x, y, and n function of x, y are homogeneous functions of the same degree, then the differential equation m dx plus n dy equals 0 becomes separable after we let y equals xv. So we're making a change of variable here, where this v is some unknown function, just a substitution we're going to make here. So let's prove this now. So proof. Okay, so proof, we're going to let y equals xv up here in this guy here. And we're going to have to substitute for my dy also. So let's take derivative on both sides here with respect to x. And again, we're assuming v is some function of x, and so is y. So let's take derivative with respect to x on both sides. So taking derivative with respect to x on both sides, here we're going to have dy dx. Here we have a product of two functions, so it's going to be derivative of first function. So derivative of x is 1 times my v plus my x times derivative of v, which we're calling dv dx. So it's product rule here I used. Now let's multiply both sides. I basically want to solve for dy here. So let's multiply both sides by dx now. So multiplying both sides by dx, so it'll be dx here, they'll cancel. Dx here, you'll have a v dx. Dx here, they'll cancel. So you have dy equals v dx plus x dv. Okay, now we're going to substitute into our differential equation up here with my substituting y equals xv, and in place of dy now, I'm going to write this stuff here. So let's do that. So again, in place of dy, we're going to write v dx plus x dv. And in place of y here and here, we're going to write xv. So let me write the result down here. So we get then. So we get this, mx comma xv dx plus nx comma xv equals v dx plus x dv equals 0. Okay, now we're going to use the homogeneous property of these functions. So we're assuming that they're both homogeneous of the same degree. So let's make an observation here. So note the following. Okay, so now here's an important observation. We're going to be using the homogeneous property of the two functions. So again, we're assuming that both m and n are homogeneous of the same degree. So therefore, n of x comma xv, you can think of as n of x times 1 comma x times v. So you can think of the x as acting like the t. So you can pull it out, and it'll be x to the n, and then capital N of 1v. And the same will be for the m function up here. So mxv, you can think of it as m of x times 1 comma x times v. Then I can pull the x out because it's homogeneous. So the x is acting like the t in the first examples we did. So we'll have these two things. So that's the key observation I need to make here. Again, since m and n are homogeneous of the same degree. So now we're going to substitute into star. So in place of nx xv now, we're going to write x to the n of 1v here. And in place of mx xv, we're going to write x to the n m1n. So doing that. So again, we're replacing this guy, replacing mx xv with this and nx xv with this. I'm out of space actually, so I'm going to erase some things. So I'm going to do the substitution and erase things here. Okay, so let me erase this stuff here. Okay, so after making the substitution, I get this then. Now I'm going to multiply this guy with that and with that. So let's do that. So doing that, we get then. So the multiplication, we then have x to the n m of 1v dx plus, so I'm multiplying this guy here, x to the n v n 1v dx. And multiplying this with that would be x to the n plus 1 n 1v dv equals 0. So these two guys here have dx's, and they both have x to the n. So I'm going to factor x to the n out on the left side and factor dx out on the right side on these two. So doing that, we get then. So I get this. So again, I factor the x to the n out on the left side, and I factor the dx out on the right side. Now let's move this guy here. Let's move it across the equal sign. So doing that, we get then. So we get this then. Now I'm going to divide both sides by x to the n. So doing that, we get then. So we divided both sides by x to the n here. Okay, that's going to become 1, and it'll be just a minus x left here. So let me write that here. So we get this then. Then we just need to realize we can separate the variables now, because we can get the negative x over the dx. We get these m and n guys over here, because m of 1v is a function of v, and so is this. So we can basically separate the x's and v's. So doing that, we get then. So separating variables, we have then negative 1 over x dx equals n of 1v over n1v plus v times n of 1v dv. So we separate the variables, so we're showing that the differential equation is indeed separable. So hence we're done with the theorem. So hence claim follows. So we're done with the theorem. Okay, this video is kind of long, so I'm just going to leave it there. We'll look at an example using this in the next video. So let's leave it there.